Welcome guys. So in this video we prove a simple fact about integral domain, and this fact is really simple but actually it's hard to imagine that we will have this result. So theorem is that integral domain, so finite integral domain is a field. Okay, so basically, since integral domain are already restricted into the commutative ring with identity, so all we need to show is that all we need to show is that every element, I should say every non-zero element, should have inverse multiplicative inverse. Okay, so in order to do this, so lemma. This lemma said that if A is R, belongs to R, and A is non-zero, and R is an integral domain, I should say R is an integral domain. Then we must have if K non-zero for any K belongs to natural number. Okay, so prove this fact is simple. So the reason is that suppose is this K such that A K is 0, then A K times 1 is 0. But this is integral domain, right? So either A is 0 or A K minus 1 is 0. But we assume that A is non-zero, so this tells you that A K minus 1 is 0. And then you can use this deduction, and finally you will always get A is 0. Because the K can always decrease 1, so you get A 0 contradiction. Okay, so this lemma is correct, then we can go back to prove this. So the proof is take A is non-zero in R, and we want to show that there must be multiplicative inverse. Okay, so I just compute what? I just collect a set. Basically, it's a k from 1, 2, 3 to infinity. Okay, C is finite. Because I assume that the integral domain, finite integral domain, so R is finite, so C is finite. Okay, so that means exist I and j belongs to integer such that I equals ij. So if this is not true, then definitely you will have infinite elements, then contradicts with the original assumption. So which tell you that a minus I, a times I to the j, a times a to the I minus j power, which is 1. Which tell you that a times a I minus a minus 1 is 1. So a I j I minus 1 is okay, sorry, this proof is wrong, because I cannot easily do multiplication inverse, but I can write it as this. So I can assume that j larger than I. Okay, so this is this. Let me see. Sorry, this. So integral domain, right? Integral domain. So this is non-zero. This is non-zero. So always have this. I tell you that a times a I minus a minus 1 is 1. So this is A's inverse. So a I say a I minus a minus 1 power is a inverse, which tell you that the original ring is a field. So my previous proof is not correct. Basically, you cannot assume that there is a cancel. You cannot cancel both elements in a commutative ring. So this is the computational detail, and all we need is just this easy lemma, and we can prove our result is correct. Okay, so we proved the theorem. Finite integral domain is a field. Finite integral domain is a field. Okay, so thanks for you guys.